Hi everyone. I want to start today's video off with this thread here, parallel wire or bifilar coil experiment. We went through a lot of very in-depth study on this thread. You can see it's only got 2.9 thousand views. Anyway, the point of this is I want everybody to start thinking about a wire that is the definition of bifilar is a wire that is parallel, wound parallel for the length of the wire. Okay, and what I want people to start thinking about is conventionally we would see one current in one direction. These two wires that are right beside each other would only ever have a single current going in a single direction. So say for example if we had a primary coil that was out over here, off page, not seen, and the primary coil had a magnetic field which essentially is a current that's changing in time, then the current that's changing in time would induce a voltage on this coil, and then the voltage would then allow for a current that would travel in one direction. The current would never change, and at one stage I will show a small picture of a coil in the video. It's a long video, I've got to apologise, but we'll show a picture of the coil, or at least this piece of wire in the video, to give you a second idea, to sort of remind you again of what we're trying to sort of think about here. So I urge all readers, go back, have a bit of a read of this thread. It is an important thread. Again, in transformers we have parallel bifilar wires that are wound, connected on the ends, in a transformer all the time. The two wires doubles the current for a smaller wire mass in the core. That's why they do it that way. So this thread is pretty detailed, goes into a lot of ideas, including one method of delayed conduction. So delayed conduction is a method of getting the currents to actually change in the coil. Okay, so remember, parallel wire, bifilar coil. What we want to do is we want to get one current moving that way and then the other current moving that way. So we want the currents to move in opposite directions. We've got to remember we're trying to create a standing wave. Okay, remembering that a standing wave is two different magnetic fields changing in time. Okay, so the magnetic field, essentially, if you were to think of the magnetic field as a propagating electromagnetic wave, okay, so the electromagnetic wave would propagate through time at a different amplitude. The amplitude changes over time, which is the very fundamental definition of electromagnetic induction. So our time rate of change of the magnetic fields can induce a voltage, keyword voltage, in a coil, and that voltage can then allow for a current. Okay, so moving down a little bit, not sure if there's much more I can show you here. The rest is sort of in the video. There's lots and lots and lots of different methods to sort of achieve what we're trying to achieve. This image here is a very good image to think about, one I've shown for a little while. We've had all the water that's washed up on the beach. The water has come back in a bit of a rush against the water that is then coming forward, and it creates a standing wave. So almost a vertical wall of water, a standing wave. Now the process here is when the water comes back this way and when there's water coming back this way, the two waves slap together very hard and create a very high amplitude. Okay, obviously this guy's going to have a hard time getting away from this water in time, and obviously when it hits him he's going to be in a fair bit of trouble. If you go and watch the video, that is in fact the case. Anyway, so this is really just a little bit of an introductory. I've got a lot of experiments, little bits and pieces over time that I've done for you. This video, just so that you know, This video is a long video, but it's really a beginner's video. Okay, we're trying to sort of start at the start to try and get people thinking about what the coils are doing, to get people to think about the interactions that the coils are having together, and so on and so forth. So for some people this video will be very basic, for others not so basic. For some that are very experienced in electronics and not had anything to do with this before, there might be a ton of surprises in this video for you as well. So you make the decision. I'd like to just ask, if this video has helped you, please consider a donation. Help us with our website costs and everything else, the cost of running all this and making it all come to you. Please consider a PayPal donation. Thank you. PSU through to my measurement block, through to my capacitor bank with protection diodes, through to my switching device that I've built. This is controlled by a microcontroller, controlled by the computer. So I've got one cord here which is USB power, 5 volts, USB serial through to the computer, a whole bunch of cables and everything in the background. You can see I've got it in H-bridge configuration at the moment, which may change. I probably will end up going to just a single DC pulse using only one channel here instead of all 4 channels. And then through to my machine here. Now this is just a very quick build that I've put together. These here are my secondary coils. I'm running with a Andrei Melnichenko type configuration at the moment. On the website, show here that this layer here, the bottom layer, has 84 turns. This second layer up is only half the size. Off the top of my head I forget, half of 84, which is, I think it's 43 turns. This coil here is a double layer. Okay, so it starts from the bottom here, winds all the way up and then all the way back again. Okay, so this layer here is meant to mirror this bottom layer over here. Okay, so turn for turn we're not quite spot on. 83 compared to 76, I believe. Anyway, measurements for that on the website as well. Like I say, 76 turns I believe. I think the inductance is fairly close, 412 compared to this coil over here being 394 I believe, off the top of my head. This coil here, I think off the top of my head, was about 94 millihenries, and when they are connected here non-inductively out to these terminals, I believe was much less, something like about 13 millihenries I believe. Now I just want to point something out while I'm here. This coil here is going to be my input coil. This coil over here is my experimental coil. This will be driving this coil over here. So inductively, if you think about this inductively, this coil over here is only going to work on this portion here, induce an EMF. Remembering an EMF is a voltage, so it's going to, this coil, the current changing in this coil is going to induce a voltage in this part of the coil only. This part of the coil over here, because it's non-inductive, won't see any change in magnetic field from this one until we get resonance. Okay, so when we get resonance, we're going to have a standing wave in here. These two coils, they cancel out magnetically, but the current that is traveling through these parts of the coils, remember the bottom layer and the top layer, the current will double according to all our experiments up to date and what we've been told in the past by those before us. So our current will double. Now because this coil over here has got a different inductance compared to this coil, the top layer, so the bottom layer has got a different inductance compared to the top layer here. Because that's different, we're going to see a difference in the change of current. And remembering from our research,
remembering that inductance defines how a coil carries current. So LDI dt with an EMF, a back EMF bit in there, which is epsilon. Okay, remembering the inductance is what defines the current. Remembering inductance is a definition of how the coil will carry a current. Alright, so if we've got a difference in this part of the coil compared to this part of the coil, all the equations state that Kirchhoff's law, we're going to have a different current at one node compared to another. Okay, because we have a non-inductive part here of the coil, Kirchhoff's current law, which states that all nodes have to have the same current. Okay, all nodes have to have the same current. That will not be true, and there's a very good reason for that. We've stated that in the past. The reason for that is that this part of the coil becomes a battery. Kirchhoff's current law, okay, the only time it doesn't stand is when there's a generator or a battery being placed in the circuit, and that's what we're doing here. Okay, but remembering we have to have resonance. This part of the coil has to be in resonance because we have to have magnetic fields that are traveling in equal but opposite directions at the same time, which creates a standing wave. Okay, you'll see that on the website. Alright, so more soon. I will update you with a bit more as time goes on. I think it's very important in every experiment that we do that we try to maximize what we can learn. I think that's very important in any experiment. We need to be open-minded, we need to maximize what we can learn and try to look at the most simple things that we can. The Mr. Prever experiment is an experiment that I have pushed for a long time. It's an experiment that pretty much is sort of mainstream in what we're doing now, and this device sort of follows in some ways the Mr. Prever experiment, so I've got to give credit to Mr. Prever as well. The non-inductive coils again, so this part here is wound non-inductively compared to this underneath coil. So this underneath coil here again is full layer all the way down. This top layer here again it's just halfway down, so I'm following the Andrei Melenchenko work. You can see here that the windings are in the same direction. Okay, so any time that we have current flowing one way in one, we should always have the opposite in the other winding. So if we come down here, we have our short, if you like, down here. We're measuring current coming through this direction and through this direction over here. So the current at any one of these 2 points here is being measured, and you've got to remember it's shorted here. So essentially this node down here should be the same as this node here, should be the same as this node here. Again, pointing out that our inductance in our two coils is different. Okay, we've measured our inductances up on the website. I believe 94 compared to 394, I think, from memory. At this end we've got a small load attached, and again I just want to point out we are dealing with a phenomena here that like I was saying in another video, we've got to get resonance, because this here, it's a standing wave, okay, where the turns in this coil equal the turns in this coil, which is underneath this coil. Okay, so this is essentially here, it's wound bifilar by the very definition of the term bifilar, which is parallel the length of the coil. Okay, so we have a parallel wire wound the length of the coil all the way to this last turn here. So this is, by very definition, this is bifilar here. Okay, and it's non-inductive. Okay, because again we have a short up here, this is shorted. Okay, this coil here is non-inductive with the layer underneath. It is not non-inductive with this layer up here. Okay, so half of this coil is inductive, half of this coil is non-inductive. Again, this is my driving coil. We'll go through again from PSU through to my measurement bridge, measurement block, through to my capacitive bank, which is semi-protective, load resistant. Okay, through to my H bridge, and my H bridge, you can see a signal there on the oscilloscope at the moment. And if I push this all together and try and make it nice, you can see I've got a capacitor. So the capacitor is from this end over here to this end here, and that is the small coil here. So this coil here is being brought into resonance, and because there's a difference in inductance, this coil over here will have a resonance to it as well, but it will be out of phase. It'll be out of phase for the simple reason is the inductance of this coil over here is not the same as this coil over here, so the resonance that is applied to this coil will have a phase lag, or at least a phase advancement on lag and lead, so it'll be a lead on this coil. Okay, again we're measuring the current on this block. Scope probes set to 1 times, and again, so we're set to 10 times on yellow channel, DC coupling, non-inverted. Okay, and we're on the red channel now, so channel 1, we are 10 times non-inverted and DC coupling. Okay, so this is what I wanted to point out. This is something that is contrary to some beliefs of some people. We have a huge difference in current. Okay, if we even just bring it down just a little bit so we can sort of see, RMS current here is 339. RMS current down here 124. Now if we do a quick little bit of math on that, we're looking at a difference. The difference is 215, and it's 2.7 times more current. Okay, 2.7 times more current. We're looking at a difference of 274, which is 2.7 times more current on this node compared to that node. Okay, and it's a short circuit here. Okay, so one of the coils is resonant, and then the inductance is different between the two coils. Well, we are looking at a difference in current on the nodes on the circuit. So this node here compared to this node here and this node here, compared to this node here and this node here, we have a difference in current. Okay, and again the circuit is, the circuit is brought into resonance with this capacitor, AC capacitor, and again the coil is connected to the short coil, the low resistance coil, and the low inductance coil is the resonant coil, which is resonant through the capacitor. Let's have a quick look, see if we can get some cursors happening there. Cursor, let's go. Let's go time. Okay, I just want to point out as well that this is the technique that I use for determining phase difference. Okay, and our little calculator in the above unity member calculator, if you do a search on our website, if you haven't seen it already, we've done a calculator. This is the method that's used to determine the difference in phase angle. Okay, so our little calculator there, so all we do is we take one of the waveforms, we go peak to peak, we take the measurement here, so it's 0.616 milliseconds, Okay, and then all we need to do is just bring that peak forward, take the difference here, which gives us a phase angle difference of 252.5 degrees. So at this stage our coils, the current in the coils it's not 180 degrees out of phase, which it does need to be, okay, because we effectively when it's 180 degrees out of phase, that's when our standing wave will be at maximum amplitude, okay. But at this stage we're 252.5 degrees out of phase, and as I say, that's not optimum. We're not at the optimum point at this stage. We need to do a little bit more work, a little bit more tuning, a little bit more messing around to try and get it better. But as I said in the other video, this is probably not the best way to do it. We're probably going about things not the right way, and what I mean by that is I mean that this input coil over here, which has almost the same amount of turns over here, 84 turns here compared to 76 turns over here, this driving this coil over here via inductive means, via transformer induction, okay, so this coil over here will reflect back on this coil, and I will show you that now that we've done what we've done. So we're going to take the red channel over here, we're going to try and do this without blowing anything up. We're going to drop the amplitude down, we're going to switch that channel off, we're going to make sure that we're triggering on channel 1. Okay, we're going to try and get a decent trigger going on there. Whoop, there we go. Okay, now let's see if we can do this without blowing anything up. Sometimes it doesn't like it. Okay, very careful, Christopher. Okay, now on the scope there you can see something that's very odd. We do have a DC offset there, you can see that. If we set the cursors to, instead of time, if we set it to voltage. Okay, so that's about our peak. It's about 0, so according to this here, if we take our probe to 1 times instead of 10 times, because we were doing current, back to cursor. So according to this, from approximately 0 there, down a bit there, according to this we have 2.4 volts above 0 line. Okay, and if we move that down, we have 3.6 volts. So there's a little bit of DC offset there in this setup. We have a maximum of 5.8 volts. Now this is it's an odd setup. Now you got to remember we're 3.3 volts on the PSU, but this little dicky bit in here is a bit odd. We've got to figure out why we're getting that, because if we disconnect the DUT, if we disconnect the device under test and check our output, we don't get any of that. So we can only assume that we are getting a reflection in the form of a negative pulse come out of the machine and come back to our input over there, which is giving us a negative result. It's giving us a reflection back on our input that is negative and effectively is pushing our input up. So this video really is a sort of a well, it's just an experiment. It's really what I'm trying to show is some of the problems that you might face as you're experimenting, some of the problems that you are going to sort of look at and sort of find that are not ideal. And again, this type of device here, what I'm trying to show is an inductive coupling between the two coils, one driving the other, and then the standing wave in here. So we've got a little bit of a standing wave, but our phase angle is not enough. Okay, we need to get 180 degrees. The current that we're measuring, or that we did measure over here, needs to be much closer to 180 degrees. The resonance that we've got on this particular coil over here, it's resonant with this coil, but it's not resonant so much with this coil. The inductance versus the capacitance, the resonance here is not ideal, and that is because the inductance difference again. So we've got a little bit of work to do. We need to find out why the reflection's coming back. Again, an H-bridge for this particular device is probably not the best. However, in saying that, an H-bridge is something that I have used right from the early days. An H-bridge, you will find if you go back through my research, is something that I pretty much started off with. When I started finding all these things, this is what I sort of found, and it's extremely interesting to find it. I just want to show you something else, a bit off topic, so I'll pause the video and we'll come back in a minute. Okay, so back again. What we're looking at here is I was going to say failure to communicate. No, what we're looking at here is we're looking at the waveforms of current again. So what we've done is we've put the probes back on the current measurements. We've dropped the capacitor, so we've now no longer got any capacitor connected. We have a small load over here. We're not getting anything out, but what we're looking at is we're looking at the current between these two coils. Okay, and through the measurement block here, through the double metal strip, I always forget the name, metal strip resistors here, very little inductance. They're very good resistors, but they only measure low currents, no good for high currents. 0.1 ohms. Again, I've been through it before, so if we have the probe on 1 times, and we can go in, and if we set our measurements on 10 times, which I need to do there, I always go one past it, and then what we can do is we can take our mean or RMS as the current. So that's currently, you would say that the current there on the channel 1 is, because it's AC, is 57 milliamperes. You get it? Poor old brain, gee whiz, not enough coffee this morning. Anyway, 57 milliamperes. Now you can see by looking at the waveform there that our currents are much further, much closer to 180 degrees out of phase. So what we have there is we have a coil combination that is 180 degrees out of phase, and you can see here, which is quite astounding at this point in time, that our even though it's 180 degrees out of phase, that our current is fairly similar. So we've got 57 up here, we've got 56, 57 down here, milliamperes. Now this is not resonant. Okay, all I've done is I've just cranked up the frequency just a little bit just to show you. You can see that there is a curvature in the waveform, up and down, and this is the normal curvature that you would get in a coil, as the inductance and capacitance along with the reactance takes time for the inductor to charge. Okay, so this is the time, and it's a curvature. It's not a linear process for the inductor to charge, so that's why we have a curvature there in the current. Okay, we've got to remember that coils and capacitors take time to ramp up and ramp down again. It's normally an exponential process as far as my simple mathematics is aware. Okay, so I just wanted to show you that. Again, our coils are much closer to 180 degrees out of phase. Remembering that there is an inductance and a turn difference in our coils. The inductance and turn difference and also a resistance difference should give us a difference in current, but at this stage the current where we are tuned is the same. So this node here, this node over here, this node here is all the same. Remembering this part is non-inductive, this part over here is inductive. So from our input over here, this part over here is the only part that's being inductively coupled. This part over here is non-inductively coupled. Now I just want to point out real quick again, in the past you'll see most of my coils are super huge coils. You'll see lots and lots and lots and lots of turns on them, and there's a very good reason for that. I don't want to go into that yet, but I just want you to keep that in mind. What I'm showing here, that this coil here is only one layer, 86 turns, and a half a layer, which is 43 turns, and inductively driving it from this coil over here. So please keep that in mind, because that is an important thing for what's coming up soon, and some of you already know why that is. Okay, so back to what we're talking about, the waveforms, the current through the coil. So if we were to draw a straight line down here, and we say, right, we've got a hose that's down in this direction, and the water in the hose is going this direction, then that would be the case for only one of these coils. What we'd have to do is bring a hose back the other way, back the opposite way, and say one current's coming this way and one current's going that way. Okay, so the current coming up this way is the same as the current coming back this way. That's because we're not in resonance. Even though we have 180 degrees out of phase, there is no resonance in the coils. Okay, so amplitude's at minimum. We're only dealing with a very low amplitude, which is 57 milliamperes, and that's almost the same on both. Even our mean values are approximately equal. Okay, so again, we have two directions of current, one coming up this way, one coming back down this way. Okay, this coil, this part of the coil, non-inductive, out to the load. You can see at this stage that we have no light on the load, that there's nothing there. Now the output voltage, okay, if we were to quickly measure that, let me pause the video one sec. Voila, the magic of video. Output voltage, we're not even dealing with a whole volt. So again, there is nothing in these coils. These coils, there's no voltage, there's very little voltage, very little current. So the inductive coupling from this coil over here, which again is being driven at 3 volts. Okay, so we've got approximately 3 volt flip-flop on this coil over here, so it's flip-flopping that's what the H-bridge does, flip-flop, so it's, if you like, it's alternate DC current is probably the best term for it, which drives this coil 3.3 volts alternate DC current, which is inductively coupled to this coil at a frequency that is not the optimum frequency, but we still have current which is 180 degrees out of phase. Okay, so our coils here are showing 180 degrees out of phase. If we were to get the voltage up on these coils, if we were to increase the voltage to get the, remembering that V over R equals I, so if we want a reasonable current out of this coil to drive a load, if that's what we want to do, we've got to get the voltage up. Okay, so the coupling at the moment between these two coils is poor. We don't have enough voltage, which therefore we don't have enough current. And again, I just want to go through, I've been through this a billion times and I'm sure you're sick of it, but the changing current in this coil determines the voltage in this coil. Okay, it's back to front. So changing current creates a voltage, and then when the voltage is there, then we have a current. Okay, and at the moment we only have very little voltage. So the various different ways what we could do to improve this setup is, what we could do is we could take this coil, we could put it over here, we could drop the turns on this coil and still put it over here, or keep it over there, but by increasing the inductive coupling by putting the coil over here would be one way to get the voltage up in this coil. And also by lowering the turns, we could increase the voltage on this coil over here, You've got to remember, as you increase the voltage, you quite often increase the current in some situations, at least until you get to resonance. Once you get to resonance, then the current will drop. So there are various different ways to do it. At this stage, this experiment, I will do a few more things, and then what we'll do is sort of make steps ahead. But at this stage, what I have shown is the direction of the current in the coils, which this part here is non-inductive, gives us a different coupling coefficient. Okay, it gives us a different coupling between here and here. And we'll do some math on that in a minute. Alright, so we're back again. What I want to just very quickly do is, as I said, just do some quick visual math, if you like, if you want to call it that, on the DUT, on the device under test, DUT. So what we're looking at here is we're looking at 3.3 volts on the input. Okay, that's what's coming out of our PSU. At the moment there's no measurable current. I'm sure there is current there, but there's no measurable current on that particular device. It's obviously down in the milliampere range. On our output, currently we have 1.46 volts according to our meter. Now these meters are really good little meters. They're not advertised as RMS, but the meters themselves are very good, very accurate little meters. This is our current. We've still got our probes on the current block there, okay, and we've still got the same setup. So throughout, the whole setup is still the same. We haven't changed it. Okay, so probes are on the current block. That is our current waveform. I'll expand it out a little bit so we can see a bit better. Okay, again, these are milliampere range, so cyclic RMS. We're looking at 104.7 milliamperes, 103 down here, so there is a little bit of a difference at the moment. Mean values are very different. Mean values are almost positive and negative different, which is an interesting result because we've been through mean and the average time above the zero line and the average time below the zero line. If you were to subtract it, so 1 plus -1 would equal 0, and if we had an exact figure above and below, then the mean value would be 0. But the mean value in this case, we're looking at -2 compared to almost 3. So we're looking at quite different values in this situation, which is very interesting. Okay, so back to our voltage reading. If we were to visually say, right, well, we know we've got 3.3 volts, which is alternating DC current on the terminals here, driving this terminal, then we've got an inductive coupling from here to here, and on our output at this particular frequency is only 1.4 volts. You have to forgive my bad math. When I haven't had enough coffee, I'm shocking. Anyway, so I just wanted to show you this stuff. We're getting somewhere. These are the very small things that we need to document, need to keep an eye on. Looking at what makes this improve. And the question, what does make this improve? What are we looking at here? What is our goal? Our goal is to turn a couple of coils into a battery. Or a generator. A generator is probably a better term, and I try to always put generator in quotes. The reason being is energy is not generated at all. There's no such thing. Science tells us that you cannot create energy from nothing, and that's what generation of energy implies, because it's simply not true. The energy is already there. The energy is in the coil. in the form of electrons. Every single piece of charge in that coil is free to be manipulated by a magnetic field and shoved down the wire. Okay, and that's the important thing. You've got to remember that what we want is we want all the charge, all the electrons, all the charge, anything that will move to come out on the terminals of the coil, and that's why we've got to have our ends bared of the coil. If we connect our connections up here where there's insulation, then no charge can flow. Okay, the insulation is it's just that, it's an insulator from the charge. The charge has to be bared on the terminals, and then we will get electricity flow through the load in the form of current and times voltage over time. Okay, watts, you've got to remember watts is a product of time, joules per second. Okay, so what have we learnt? What are we learning? We are learning that the standing waves, magnetic resonance, 180 degrees out of phase, can pump current, and we've seen from our experiments so far, we've seen that there can be a difference of current on the terminals from one node to the other. So these nodes are essentially, it's all the same piece of wire. There's no way that we should see from this node here to these two nodes here through the same piece of wire, and only a tiny little bit of resistance, 0.1 ohms on each one of these measurement resistors. There's no way that we should see such a difference in current, because like I said, it's the same piece of wire. We shouldn't have any difference, but we do. Okay, and that's the resonance, the inductance, and everything making this coil change its properties. We are, through resonance, through inductance, through capacitance, we're making the coil change its properties and then become a pump for current. But you've got to remember, the current will only flow, and we showed that before, current will only flow if there's a voltage there. And in this case, we're looking at a voltage of 1.465 volts. And obviously the point is to get the voltage up. Voltage must be up before we can make the current flow. Okay, because remember Ohm's law, V equals I equals V over R. So I being the current, V being the voltage, R being the resistance. I think this video is probably long enough. I do apologise, I'm rambling a little bit. Let's aim for a little bit higher or a little bit better result in the next video. Next video will be coming soon. Thanks guys.